Okay guys, we're going to be doing a fluids PowerPoint to start off the notes for our first at-home section of physics here. We were originally going to do magnetism if we were at school, but that would be really, really hard to do via the internet, as you'll see why later on. So we'll talk about fluids. Alright, so a fluid is anything that can flow. So a fluid can be a liquid, a gas, or just a stream of solid particles. Viscosity is how much a fluid resists flow. So something like syrup has a high viscosity and water has a relatively low viscosity. A Newtonian fluid is something that behaves like you'd expect a fluid to behave, meaning that the viscosity stays constant, it doesn't change much. A non-Newtonian fluid is when you have something that the viscosity changes based on how forces are applied. So for example, if you've ever seen videos of people walking across like cornstarch and water, that is acting as a non-Newtonian fluid. When you apply a force, the viscosity gets increased quite a bit, so you can actually walk across it. Alright, density or fluid density. The density of a fluid usually has the symbol rho. It's like a P without a hat. That's the Greek symbol rho. And the units for density in a fluid and SI system are kilograms per meter cubed. Specific gravity, I call it stupid density because it's just like density, except it's divided by 1,000. So fluid density just means the density of a fluid compared to the density of water, and water has a density of 1,000 kilograms per meter cubed. So for example, if you had something with a density of 1,500 kilograms per meter cubed, its specific gravity is 1.5. That should say specific gravity, not specific density. So that should be specific gravity. All right, pressure is just the force per area that something applies. So it's just pressure is equal to force over area. Unit for pressure is going to be a Pascal. And pressure in general, like if you have something that punctures your skin or does damage to your skin, pressure is going to be what does it. So if you step on one nail, it will puncture your foot. If you step on a board filled with a lot of nails, you'll usually be okay, because the pressure of the one nail is significantly greater than the pressure of the many nails because the area is much smaller. Right, incompressible fluids. Liquids are incompressible fluids, meaning pressure will not increase their density. However, gases are not incompressible fluids, and in general, streams of solid particles will be incompressible as well. Right, for pressure in a fluid, the deeper you go into a fluid, the pressure of the fluid applies increase, and like the shape of what you're in doesn't matter. So if you look at this diagram down here, the pressure at points A, B, C, and D are all the same, independent of what the shape of the container is above them. And it's applied equally on all surfaces. So if you have the pressure at this point, it is equal to the pressure on this wall at the same point. So it doesn't matter whether the surface is vertical or horizontal, the pressure on it is the same. Atmospheric pressure is about 15 pounds per square inch. So if I hold my arm out, that means the atmosphere is pushing down on my arm at 15 pounds per every square inch. So that'd be about 150 pounds. I cannot lift 150 pounds with my arm just holding it out like that. The reason I am able to hold my arm out like that is that atmospheric pressure is pushing down in all directions. So it's pushing vertically up and down and horizontally right and left. So it pushes in all directions. That does mean my body is also pressurized to 15 pounds per square inch. So for example, if I go on an airplane and go cruise at 30,000 feet, the external pressure decreases, but my internal pressure stays the same. So your body actually expands a little bit because as the exterior pressure goes down, the interior pressure of your body stays the same and it pushes out. And you can see this in a couple different ways in an airplane. If you take your shoes off before you take off, you will find them looser or tighter when you get to altitude. So if you take your shoes off on the ground, you might not be able to put them back on when you're at 30,000 feet. Other way you'll notice is everything at ground level is pressurized to that 15 pounds per square inch. So for example, if you have like a bag of chips, it will puff up and get really filled with air when you get to higher pressures, because inside the bag is 15 pounds per square inch. Outside the bag is still is less than that, so it expands. Gauge pressure versus absolute pressure. Gauge pressure is the pressure that something has with all the external pressure of fluid subtracted from it. So that means you're not including things like atmospheric pressure, any fluids above what you're talking about, anything like that is just the pressure of that system you're talking about. Absolute pressure includes all external pressures. Usually we're just including atmospheric pressure again. So it's gauge pressure is usually without atmospheric pressure. Absolute pressure is with atmospheric pressure. All right, the equation for pressure at depth in a fluid. So we'll be using this when we talk about do math with this stuff. So pressure is equal to rho GH. So pressure equals fluid density in kilograms per meter cubed. Acceleration due to gravity, it's going to be positive, kind of like it has been in the past. And H is the depth of the fluid. And the units for that are pascals, and a pascal is a Newton per meter squared. So that's 1 pascal is 1 Newton of pressure over a whole square meter. So it's actually a relatively small unit of pressure. This is my favorite pressure joke. So Newton, Einstein, and Pascal were playing hide and seek. Einstein was it and started counting to 20. Pascal ran and hid. Newton stood in front of Einstein and drew a box around himself in chalk. When Einstein was done counting, he found Newton right away, so that was a terrible hiding spot. Newton said, but you didn't find me. You found 1 Newton per meter squared. You found Pascal. All right, so some questions about fluid pressure. So 15 pounds per square inch of air is pushing down my arm. When I try to lift it, how am I able to lift it? Like we said in the notes, even though there's 15 pounds per square inch pushing down, there's also the same amount of force pushing back up. So it doesn't matter what the pressure is externally applied by a fluid to your body, because it's going to cancel out with the up and the down forces. Number 2, high pressure is what causes your skin to be penetrated by an object. Based on this, why is it better to lay in a bed of nails than a single nail? If you lay in a bed of nails, the total area of all those nails is increased. Let's say there's 1,000 nails that you're laying on. The area is increased 1,000-fold over just laying on one nail. And since pressure equals force over area, sorry, I'm drawing that with my finger, so I'm doing my best. Pressure equals force over area. If you increase the area, the pressure goes down. So they are inversely proportional. So the more nails you have, the more area you have. Even though the force is the same, the pressure from each nail goes down. So true or false? Due to the pressure deep in the ocean, it is harder to swim up to the surface. That is false. So the deeper you get into a fluid, the pressure external to your body does increase. So your body tends to kind of like, if you get deep enough, your body can be kind of crushed by that in your lungs and things like that because you're pressurized at 15 pounds per square inch. However, the ocean is pressurized, or as you get deep into the ocean, the external pressure becomes greater than that. But it does not become any harder to get to the surface because, again, let's say you're at a certain depth and the pressure on you is 100 pounds per square inch. That's pushing down and up on you at the same time. So it doesn't become harder to get to the surface, just your body becomes more squished together. Right, would the pressure be greater 4 inches below the surface of a glass of water or 4 inches below the surface of Lake Michigan? And again, the container doesn't matter for pressure at depth in a fluid. All that matters is how deep you are. So the pressure is the same 4 inches below the surface of a glass of water or 4 inches below the surface of Lake Michigan. So the pressure is the same in either situation. And last question, this is kind of a repeat. Is it harder to swim when you're in deeper water because the pressure is greater the deeper you go? No, it's the difficulty of swimming up or anywhere is going to be the same because the pressure is applied equally in all directions on your body. All right, so that's it. There should be a short quiz on Moodle about this. You'll get 5 questions. There'll be 5 random questions based on the PowerPoint. You are welcome to watch either the video again if you need to, or use the PowerPoint that's posted on Moodle to do that quiz. Tomorrow, we'll be doing the second half of this PowerPoint, another 15 slides, should take about the same amount of time. Then we'll move on to doing problems. This is kind of a side note, guys. I'm kind of starting out slow because I know this is new for everyone. So first day should take about 15 minutes or so for, I would guess, for you guys to do all this. But don't expect that to be the time frame from here on out. But we'll kind of experiment with it and see how it goes. And if anything goes wrong, feel free to email me or post questions on the message boards on Moodle is probably the best way, so that way I don't have to answer questions a ton of times. Other than that, I will have another one of these videos for you guys tomorrow. Thanks.